So sometimes it's rather easy to take figures or data like this, which shows the increase in CO2, which is very monotonic, as we said, because it's an inert gas with long residence time, and look at temperature change with respect to some base period. So here is the difference of global mean temperatures from the 20th century average, which shows that the temperatures were cooler than the 20th century average before about 1940, and they started jumping around the zero line and then have been warming since the 1970s and 80s. And then the warming is not as monotonic as the CO2 increase. So the merchants of doubts then show this and say, look, the CO2 increase has nothing to do with the warming. But what is missing, of course, in this fallacious argument is that the additional energy that is trapped by the increase in CO2 and other greenhouse gases that we will see in a minute is used for evaporating from the oceans, because a warmer atmosphere has a higher capacity to hold moisture, and the additional energy is taken down into the ocean, which is the main purpose of this book, to look at ocean's role in climate change, especially this chapter that we'll come to a little bit later on. We have also looked at it in the earlier part of this course, and the energy is also used for melting glaciers. So we have to be sure that we are not going to fall for fake arguments. So the year-to-year variability also is related to things like El Nino and La Nina we looked at, where during La Nina and normal times the ocean is soaking up heat, and during an El Nino it is releasing it, and there are volcanic eruptions happening along the way as well. So if we look carefully, then we will see that all those natural variabilities like El Nino and La Nina, and natural forcings like volcanic emissions and so on, and the use of energy for warming the oceans, warming the atmosphere, melting the glaciers, evaporating the water from land and oceans and lakes and so on, are all going to create this ups and downs. But it is very clear that despite the ups and downs, the temperature is warming. And an easier way to see is that the year-to-year variability can dominate in this kind of plot, but you expect that the low frequency variability or decadal average warming has to increase. So that is shown here clearly, that each decade before the 1940s was cooler than the 20th century average, but since then each decade is warmer than the previous decade, even though year-to-year anomalies can be up or down. So this you can use to run away from the merchants of doubt that there is no lack of evidence at all that CO2 and other greenhouse gases are coming from human activities. Additional energy is being trapped, and that energy is creating global warming, which in fact is accelerating. So you can see that the increase from the 60s to 70s, 70s to 80s, 90s and so on is larger and larger. So the warmest years on instrumental record, the top 5, 6, 7 have all happened in this decade of the 2010s. So there is no good news coming anytime soon. So we also have to then look at other greenhouse gases we are emitting along with CO2. So here we are looking at what is called radiative forcing in watts per square meter, and the annual greenhouse gas index as well. So we will see what this means. Basically, we are increasing CO2 the most. So when you increase a greenhouse gas, incoming shortwave energy from the sun is creating outgoing long-wave energy from the surfaces, in addition to the increase in water vapor, which is also a greenhouse gas. So the energy that is trying to go out of the atmosphere to space and from the surface to space is being trapped more because of increasing greenhouse gases. So that energy imbalance is what we call radiative forcing. Anything that perturbs the top of the atmospheric energy balance, like volcanic forcing, aerosol in the stratosphere and so on, can be called radiative forcings. So we see that the the index of annual greenhouse gas is pegged to 1990 to be 1. We were below that before 1990, but now we are jumping up cats and dogs above that. Okay, so you can see that most of the greenhouse gas index and radiative forcing is coming from CO2, but we are also increasing methane, which is a little bit more complicated in terms of sources and sinks and its trend, because it comes naturally from wetlands and peatlands and also permafrost and rice paddy cultivation, cattle, and so on. Nitrous oxide, which comes from agricultural activities. CFCs are the refrigerants, and HCFCs and HFCs are the refrigerants as well. Obviously, we replaced CFCs or tried to replace CFCs during the Montreal, based on the Montreal Protocol, because they are harmful for the ozone hole. But then HCFCs and HFCs turned out to have much larger greenhouse effect as well. So when we have multiple greenhouse agents like this, we also have to see how much greenhouse warming they create. So just like a greenhouse gas index, we also create what is called a global warming potential. So we peg the CO2 radiative forcing impact at 1, and then we compare the global warming potential of other greenhouse gases to that. So when we want to worry about greenhouse gases, we have to worry about the concentration, their concentration, so how much is present, and their residence time, so how long they last, and how much more potential they have for global warming. Okay, basically you take same amount of greenhouse gas and compare its forcing over a period like 100 years to CO2 to say how much more global warming potential it has. For example, methane concentration will be seen soon, but methane has about 25 times the global warming potential of CO2. But whereas CO2 lasts for multiple centuries, methane has a residence time of about 12 years in the atmosphere. So these are the things we have to worry about. So here, looking at the warming influence in watts per square meter of the various gases, again setting 1990 to 1, we are looking at the annual greenhouse gas index now, giving the reverse sense as here. So we are just plotting the same thing, showing CO2 is got the greatest greenhouse gas index, and then you have methane, nitrous oxide, CFCs, and HFCs, and 15 other gases. You can also look at the radiative forcing in watts per meter squared for each one of them in this way. Since the Industrial Revolution, carbon dioxide has produced a positive forcing, so it is trapping more energy. Methane has produced a positive forcing. CO2 is the largest, as we said before, but there are uncertainties in these estimates. Halogenated gases, negative radiative forcing, because some of these gases destroy ozone, so that changes the radiative budget. So it's not good news, but it produces some cooling in the radiative forcing sense. Nitrous oxide has a positive forcing as well. So these are the long-lived greenhouse gases. In the US, they tend to say long-lived. In India, we say long-lived. So short-lived gases that create ozone or create or destroy other greenhouse gases are shown here, and so that they include sulfur dioxide, black carbon, and gases, so some other things that are included there. Aerosols, solid or liquid particles, changes in clouds due to aerosols. You can see that the uncertainty is high here. Black carbon is absorbing, so it produces a positive effect, but there are other aerosols like sulfate aerosols which can have a scattering and cooling effect. Changes in clouds, high uncertainty there, as you can see, but the best best estimate we have is on the negative side. Change in albedo due to land use, so deforestation increases albedo, so that may be cooling a little. So change in energy from the sun is very, very small compared to all these, which is also sometimes used to confuse people. So the net total due to human activities is now at over 2.5 watts per meter squared since Industrial Revolution. That's how much additional energy we are trapping, and we will see that 93% of this additional energy is going into the ocean. So ocean has a massive role to play in controlling the global warming rate, because how much energy remains in the atmosphere determines how fast the atmosphere warms. So ocean obviously has a huge role to play in moderating global warming, and we'll see that ocean also takes up about 25% of the CO2 that is being emitted from fossil fuel burning and so on. So we have to consider all those things. But ocean is also getting acidified, and the warming ocean also begins to have reduced solubility of CO2, so that also has to be considered. So monitoring to see whether ocean continues to be a sink of CO2 and whether its ability to absorb CO2 is decreasing because of the warming and so on, all have to be considered. Additional factors are there. For example, warmer ocean and changed circulation are also reducing oxygen in the ocean, especially in some parts where deoxygenation is seriously perturbing the ecosystem, the marine ecosystem. Some fish are being replaced by jellyfish, for example, and so on. So which ecosystem responds better to such perturbations is always critical, especially in terms of what is the human food source from the oceans. Of course, there are also ecosystem impacts on land, but we have already looked at that in the other parts of this course. Okay, so we'll come back and look at other parts of the ocean's role in climate change to conclude this chapter. Okay, see you in the next podcast.